Hello everybody, Mr. Hennon here for another little Hinstitute video. In this one, we're going to look at what happens when forces are acting on an object, but they're acting at an angle as opposed to perfectly vertical or perfectly horizontal. And then we'll also look at objects on incline. So I'm going to start. I've got this picture of a wagon here, and let's just imagine that some kid comes along and they apply a force on the handle, so they're pulling on the wagon in this direction. Um, I'm just going to call this F applied, so FA. And then we also know that we definitely have a weight to my wagon, so there's going to be a force pulling this thing down. So I've got an FG acting on it. And then there has to be a normal force. If this is on some kind of surface here, we know that if there's like a road or ground or anything, that the ground is going to push up on it, so it's going to apply some upward force. So I'm going to have a normal force acting up on this thing. Call that Fn. And I call that the normal force. We'll talk more about that as we deal with it. I had mentioned before, that basically means that it's perpendicular to the actual surface. So other things I would need to know is something about the angle that's actually acting over here. So I'm going to put a little angle in here. I need to know what that theta is. So before I can actually tackle this, since I've got Fn and Fg perfectly vertical, I need some vertical forces to go with it and some horizontal forces to go with this particular setup. So what I'm going to end up doing is taking my Fa and splitting it up into those two little pieces. So for example, I would start out and we're going to split, let's do some purple here. We're going to take FA and we're going to find its horizontal component. So we're going to figure out how much is it pulling forward on this object. I'm going to call this FAX. So that's a horizontal component. And then also we need to figure out how much it's being pulled up. So we're going to find an FAY, like that. So this orange kind of vector and this purple vector, those aren't new vectors that are acting, those are components of my applied force. So the key thing that I have here is I can use good old SOHCAHTOA to kind of relate those three things, because this FA, even though it's going to act over here, we could put it over here to kind of show that it creates a nice little triangle, nice little right triangle. So as I kind of go about trying to relate these things, since FAX is adjacent to this angle and FA would be the hypotenuse of this angle, we can actually find FAX by taking FA and multiplying by the cosine of my angle. So what that does is that figures out how much force is actually pulling the wagon forward or horizontally. And then we would do the same thing with my FAY, my vertical component. It's going to be FA times the sine of the angle, since it would be, so when I look at it from this picture, the little dotted line, it's opposite it. So that's the main thing that we have to do. And then other things that we can kind of figure out. Let's say that this had some particular mass to it. So this has a mass. Then I could actually figure out what the acceleration of this object is, because it has a horizontal component or a horizontal force of FAX to the right. That's the only force, that would be the only net force that would actually accelerate this thing. So I could actually figure out the acceleration using F equals ma, but the F that I would put in here would be the FAX, and then I would divide that by the mass of the object, and that should figure out my acceleration. The reason I'm using the FAX is there's nothing that's opposing that. So we're assuming this is a nice little frictionless surface, or the wheels are rolling well enough and we don't have to worry about it. Now vertically, it's not moving up and down. So we have to have any upward forces equal any downward forces. So if you noticed, when I drew in my nice little Fn here, I made it smaller than Fg. And there was a reason I did that, because technically both of these forces together should equal the Fg. So as I kind of think of this particular setup, Fn is acting upward, Fay is acting upward. So those two added together should equal my force of gravity, which is the downward force. So if I knew if I knew the mass of the object and I knew how much they applied and what angle, I could figure out the weight of the object, which is the force of gravity. I could figure out how much is pulling them forward, how much is lifting them up, what the normal force is, what the acceleration, all that lovely stuff. So that's the first part of looking at forces acting on an object. Now what I'm going to do is I'm going to totally change topics here. Let's just get rid of everything. Wish I had my whiteboard, it would erase much better. And now what I'm going to do is I'm actually going to take this wagon, I'm going to put it on an incline. So I'm not going to apply a force at an angle. Instead, I'm going to look at what happens when I actually have it on something that's inclined at an angle. And so we're going to get kind of a slightly different situation here. So let's start out, let's say that I have some incline here. So I just make a giant incline, and just to make it easy, it's going to be inclined to some angle theta. So that's the idea. Let's put our wagon on here again. So here's our wagon. Let's put red on there. There we go. Okay. Now I'm going to draw the forces acting on this. So the most obvious one is there's going to be a force of gravity. So gravity is going to pull this wagon, but like we talked about before, it's going to pull it straight down. So our force of gravity is going to act like this. So it's acting straight down. So it's actually kind of tilted with the fact that you're on an incline. That can't be the only force, otherwise the wagon would be falling straight down. So the other force that we have is that normal force. In other words, the surface here, this surface right here, is going to hold the wagon up. But remember, I said normal force meant perpendicular, so the normal force would be acting in this direction, like this. Those are not opposite each other. They are not equal to each other. So how do I go about solving this type of problem? Like, what exactly am I going to do? So the main thing we're going to try to tackle with this is we're going to take this weight and we're going to break it up into how much of the weight is holding the object on the incline and how much of it is pulling the object down the incline. So these two vectors I just drew, I'm going to change the color here so we can kind of see it. So let's make this one purple. This one is going to be F perpendicular. So it's a force that's perpendicular. So one of the things that the force of gravity is doing is it's holding it onto the incline, but it would be perpendicular to the actual surface of the incline. The other force here, let's make this one this color. So make it go in here. This one is how much of gravity is pulling it down the incline. We always think of gravity as pulling things down, but if the incline is there, it's getting in the way. This is going to be parallel to the surface that's trying to pull it down. So what we're basically going to end up doing is we're going to use the purple one and the orange one here instead of actually using our green force of gravity. So I need to figure out how do I find those two. Here's the neat thing. This angle that's sitting down here that we kind of pointed out earlier. There we go. That actually pops up over here. It happens to be sitting right here. This would be the same angle. So this angle and this angle are the same. So I can actually find F parallel by thinking of it as actually acting down here. And now I have a nice little right triangle. It's opposite the perpendicular is adjacent, so I'm going to write these out. So F parallel would actually be the force of gravity times the sine of my angle, and F perpendicular would be the force of gravity times the cosine of theta. So that allows me to split that gravity or that force of gravity into a perpendicular component and a parallel component. Then I can do other things. For example, the neat thing is normal force actually met perpendicular. So guess what? It is equal to F perpendicular. So whatever I get F perpendicular, then the normal force will push back with that same force. They're equal in magnitude, they're just opposite in direction. Then the other part, if I was trying to find the acceleration of this cart, if I knew the mass of it, for example, and I wanted the acceleration, it'd be F over m, but the F would actually be the parallel force, because it would be this force is what's actually causing it to go down the incline. Assuming we don't have any friction here, or it's so minimal, we don't have to worry about it. We can solve it. That's a little bit of help. Talk to you later.